Welcome, everyone. I'm excited to kick off our presentation today. The topic is carbon and its compounds. We'll explore the fascinating world of carbon, its unique properties, and the wide variety of compounds it forms. Over the next few slides, we'll cover its different types, structures, and importance in everyday life. Let's get started. Let's take a look at some of the fascinating topics we'll cover today, starting with soaps and detergents. We'll explore how they work and their importance in cleaning. Then, we'll move on to the concept of functional groups, which are specific groups of atoms responsible for the characteristic reactions of a compound. Understanding these groups helps us grasp the behavior of many organic molecules. Next, we'll examine electron dot structures, a simple way to visualize how electrons are shared in molecules, especially in covalent bonds. This leads us into understanding some important carbon compounds, which form the basis of organic chemistry. We'll also discuss isomerism, which is all about how molecules with the same formula can have different structures and properties. Then, we'll look at how covalent bonds are formed, the fundamental linkages that hold molecules together. Following that, we'll see how a vast number of carbon compounds can be formed, highlighting the incredible versatility of carbon. We'll delve into the chemical properties of these compounds, understanding how they react and interact. We'll explore the concept of homologous series, groups of organic compounds that differ by a repeating unit, and see how hydrocarbons, whether saturated or unsaturated, fit into this picture. Then, we'll focus on the bonding in carbon, specifically covalent bonding, which explains the stability and diversity of organic molecules. We'll also look at how a very large number of carbon compounds are formed, emphasizing the richness of organic chemistry. Finally, we'll touch on the occurrence of carbon in nature, showing its fundamental role in life and the environment. Throughout this presentation, these points will connect to give us a comprehensive understanding of organic chemistry and its significance. Carbon is a fascinating element because it's found all around us and in many forms. You'll find it in the atmosphere, where it exists as carbon dioxide, playing a crucial role in the Earth's climate system. It's also deeply embedded inside the Earth's crust, often in mineral forms like carbonates and hydrogen carbonates. In addition, carbon is a fundamental part of all living organisms. From the food we eat to the plants and animals, carbon forms the backbone of organic molecules. When we look at fuels, carbon is present in many common sources like wood, coal, charcoal, coke, petroleum, natural gas, biogas, and marsh gas. These fuels are essentially carbon-rich, which is why they're so important for energy production. Furthermore, carbon occurs in various compounds, including carbonates and hydrogen carbonates, which are important in geological and biological processes. And in its pure form, carbon exists as well-known structures like diamonds, which are incredibly hard, graphite, which we use in pencils, and fullerenes, which are fascinating molecular cages with unique properties. Overall, understanding where carbon occurs helps us appreciate its versatility and significance in our environment, industry, and daily life. Let's take a closer look at carbon and its atomic structure. The atomic number of carbon is 6, which means it has 6 protons. Its electronic arrangement is 2 electrons in the first shell and 4 in the second shell, giving it 4 valence electrons. These valence electrons are key because they determine how carbon interacts with other atoms. To achieve a more stable state, carbon can either gain 4 electrons, lose 4 electrons, or share 4 electrons through bonding. However, gaining 4 electrons isn't very likely because the 6 protons in the nucleus would then have a hard time holding onto 10 electrons. Losing 4 electrons also requires a lot of energy, making that less feasible. So, instead, carbon tends to share its 4 valence electrons with other atoms. This sharing leads to the formation of covalent bonds, which are essential for building complex molecules in organic chemistry. Because carbon needs 4 additional electrons to complete its outer shell, its valency is 4. This is why we say carbon is tetravalent. It can form 4 covalent bonds. This ability to form multiple bonds makes carbon incredibly versatile and fundamental in forming the backbone of countless organic compounds. So, Understanding this bonding behavior helps us grasp how carbon-based molecules are constructed and why they are so essential in the chemistry of life. Let's start by examining how nitrogen atoms form bonds. As you can see, two nitrogen atoms share 3 pairs of electrons, resulting in a triple covalent bond. This occurs because each nitrogen atom has 7 protons, giving it an atomic number of 7, and its electronic configuration is 25. With 5 valence electrons, nitrogen needs 3 more to reach stability, so sharing 3 pairs of electrons allows both atoms to achieve a full outer shell. Moving on to oxygen, its atomic number is 8, and its electronic configuration is 26. Each oxygen atom has 6 valence electrons and needs 2 more to be stable. Therefore, 2 oxygen atoms share 2 pairs of electrons, forming a double covalent bond. This sharing helps both atoms complete their octet. Now let's look at hydrogen. Hydrogen has an atomic number of 1, with an electronic configuration of just 1, and it has only 1 valence electron. To reach stability, hydrogen needs 1 more electron. When 2 hydrogen atoms share their single electrons, they form a single covalent bond, resulting in an H2 molecule. Overall, covalent bonds are all about sharing electrons between atoms. Sharing 1 pair of electrons creates a single covalent bond, sharing 2 pairs forms a double bond, and sharing 3 pairs results in a triple bond. This sharing process is fundamental to how atoms come together to form molecules, which is a key theme in understanding chemical interactions. Now let's take a closer look at the electron dot structures for these molecules. Here, you can see the ethane molecule, C2H6, represented with its bonding and valence electrons. The dots around the symbols show the electrons involved in bonding and lone pairs. Similarly, the methane molecule, CH4, is illustrated with its electrons arranged around the carbon and hydrogen atoms. Electron dot structures are essential because they help us visualize how atoms share electrons to form bonds. They highlight the number of valence electrons each atom has and how they pair up to create stable molecules. Notice that in ethane, the carbon atoms form a single bond with each other and with hydrogen atoms, which are represented by the dots. The same idea applies to methane, where carbon shares electrons with 4 hydrogens, completing its octet. Understanding these structures is key because they give us a clear picture of molecule formation, which is fundamental to understanding chemical reactions and properties. So, grasping how to interpret and draw these electron dot structures is a vital step in mastering molecular chemistry. Let's talk about the different ways carbon atoms can connect with each other. As you can see, they can form long chains, branched chains, or even closed rings. The reason this is possible is because of carbon's valency, which is 4. This means a carbon atom can form 4 bonds with other atoms. Since carbon can bond with other carbon atoms, it allows for the formation of complex structures like chains and rings. This property is called catenation, and it's really key to why carbon is such a versatile element in organic chemistry. Because of catenation, carbon can form an enormous variety of compounds. In fact, there are over 3 million known carbon compounds, more than all the compounds made by all other elements combined. This incredible diversity is mainly because carbon can create such complex and stable structures, including long chains, branched chains, and rings. So, in summary, the ability of carbon to form multiple bonds and various structures explains why it is the backbone of organic chemistry and why so many different compounds can be built from it. Let's take a closer look at hydrocarbons and their different types. First, we have alkanes, which are hydrocarbons that contain a triple covalent bond between 2 carbon atoms. Their names always end with -un, making it easy to identify them. Next, we have alkanes, which are saturated hydrocarbons. These have all single covalent bonds between the carbon atoms, meaning they are saturated with hydrogen. Their names end with -ane. Then there are alkenes, which have a double covalent bond between 2 carbon atoms. Like alkanes, their names end with -ene. It's important to see the connection here. Alkenes and alkanes are both types of hydrocarbons with multiple bonds, and we often refer to them collectively as unsaturated hydrocarbons because they have double or triple bonds. In contrast, alkanes with only single bonds are called saturated hydrocarbons. All these compounds contain only carbon and hydrogen atoms, making them hydrocarbons. Understanding these differences is key as we explore how hydrocarbons behave and how their structures influence their properties. Let's take a closer look at some examples of isomers. On this slide, you can see the structural formulas for normal butane and isobutane. Although they both have the same molecular formula, C4H10, their structures are different. Normal butane has a straight chain, while isobutane has a branched chain. Moving on, pentane, which has the molecular formula C5H12, has 3 different isomers: normal pentane, isopentane, and neopentane. Similarly, butane has 2 isomers: normal butane and isobutane. The key concept here is that these compounds share the same molecular formula but differ in how their atoms are arranged. This property is called isomerism. It's a fascinating aspect of organic chemistry because these differences in structure can lead to different properties and behaviors in the compounds. So, in summary, compounds with the same molecular formula but different structures are called isomers, and this phenomenon highlights the diversity and complexity of carbon compounds. It's a fundamental concept that helps us understand how different arrangements can impact the characteristics of these molecules. Let's look at some common examples of functional groups and their naming conventions. For aldehydes, we have HCHO, which is methanal, and CH3CHO, known as ethanal. Notice that aldehyde names typically end with the suffix -al. Moving on to ketones, an example is CH3COCH3, called propanon, and CH3COC2H5, which is butanon. Ketone names usually end with 1. Now for alcohols, an example is CH3OH, or methanol, and C2H5OH, ethanol. These compounds end with -al. When it comes to acids like HCOOH, which is methanoic acid, and CH3COOH, known as ethanoic acid, the key is the suffix OIC acid. Finally, for halides, we have compounds like CH3Cl, chloromethane, and C2H5Br, bromoethane. The halogen groups attach to the carbon chain and are named with the suffix -ane, preceded by the halogen name, such as chloro or bromo. A crucial point to remember is that a functional group is essentially the part of the molecule that determines its chemical properties. It's like the identity card of the compound. Understanding these groups helps us predict reactivity and behavior, which ties back to our overall theme of understanding organic chemistry. Let's take a closer look at some of the alkanes, which are part of the homologous series. Starting with methane, which has the chemical formula CH4, it consists of 1 carbon atom bonded to 4 hydrogen atoms. Moving on to ethane, C2H6, we see it has 2 carbon atoms connected by a single bond, with 6 hydrogens attached. Propane, with the formula C3H8, has 3 carbons in a chain and 8 hydrogens. Then butane, C4H10, which extends the chain further, and pentane, C5H12, with 5 carbons. The key point here is that these compounds all follow a general molecular formula of CnH2n+2. That means, for any alkane, if you know the number of carbon atoms, you can determine the number of hydrogen atoms. Their names all end with the suffix -ane, indicating they are alkanes. Now, moving to the concept of a homologous series, this is a group of compounds that share similar structures and properties. The members of this series differ from each other by a repeating unit, which is a CH2 group. So each successive member in the series has 1 more carbon and 2 more hydrogens than the previous one. This pattern makes it easier to predict properties and understand how the series evolves. Understanding these concepts helps us see the bigger picture of organic chemistry and how different compounds are related through these systematic changes. Let's explore some key chemical reactions involving carbon compounds. First, substitution reactions. For example, when methane reacts with chlorine in the presence of sunlight, it forms chloromethane and hydrogen chloride. This process is called substitution because one atom, in this case hydrogen, is replaced by a halogen atom. Similarly, chloromethane can react further with chlorine to produce dichloromethane, and so on. Saturated hydrocarbons, like alkanes, can undergo substitution reactions with halogens to form various substituted products. Next, we have addition reactions, which are typical for unsaturated hydrocarbons like alkenes. In these reactions, hydrogen adds across the double bond, converting an unsaturated compound into a saturated one. For example, ethene reacts with hydrogen in the presence of a nickel or palladium catalyst to form ethane. This process is called hydrogenation. The catalyst helps the reaction to proceed smoothly at lower temperatures. So, unsaturated hydrocarbons readily undergo addition reactions with hydrogen to become saturated hydrocarbons. Moving on to oxidation reactions, alcohols are a good example. When alcohols are heated with strong oxidizing agents like alkaline KMnO4 or acidic K2Cr2O7, they get oxidized to carboxylic acids. For instance, ethanol can be oxidized to ethanoic acid. This process involves the loss of hydrogen and the addition of oxygen, transforming the alcohol into a more oxidized form. Finally, let's talk about combustion. Carbon compounds, whether they are hydrocarbons or alcohols, tend to burn in oxygen. When they do, they produce carbon dioxide, water, and release heat and light. For example, methane burns with oxygen to produce CO2 and H2O, releasing energy. Similarly, ethanol burns to give carbon dioxide and water, along with heat and light. This process is fundamental because it releases energy stored in chemical bonds, making it vital for energy production. So, in summary, these reactions, substitution, addition, oxidation, and combustion, are essential ways in which carbon compounds behave chemically, connecting to their roles in industry, energy, and organic chemistry. Ethanol, also known as ethyl alcohol, has several important uses. It is used in making medicines such as tincture iodine, cough syrups, and tonics. Additionally, ethanol reacts with sodium to produce sodium ethoxide and hydrogen gas. This reaction is quite significant in chemical manufacturing. Ethanol also acts as a solvent, which means it can dissolve other substances, making it useful in various industrial processes. Moreover, ethanol is the main ingredient in alcoholic drinks, which is why it's so widely consumed worldwide. It's interesting to note that ethanol is soluble in water, so it mixes well with aqueous solutions. Now, let's talk about how ethanol reacts with other chemicals. When concentrated sulfuric acid, or H2SO4, is heated with ethanol, it produces ethene and water. This process involves the sulfuric acid acting as a dehydrating agent, removing water from ethanol. The chemical equation for this reaction is 2C2H5O plus 2H2SO4, resulting in 2C2H4 and water. Finally, a quick overview of ethanol's properties. It's a colorless liquid with a pleasant smell and a burning taste. These characteristics, along with its chemical reactivity, make ethanol a very versatile compound in both industrial and everyday applications. Now let's talk about saponification. This is the process where an ester reacts with sodium hydroxide solution. When this happens, you get the sodium salt of the carboxylic acid and the parent alcohol. We call this reaction saponification. It's an important reaction in soap making, for example. Next, we have esterification. This occurs when ethanoic acid reacts with ethanol, and in the presence of concentrated sulfuric acid, they form an ester called ethyl ethanoate. An interesting point here is that this ester is soluble in water, which gives it some unique properties. Moving on, let's look at how ethanoic acid reacts with carbonates and hydrogen carbonates. When ethanoic acid encounters substances like sodium bicarbonate or sodium carbonate, it produces a salt, sodium acetate, along with water and carbon dioxide. This reaction is quite common in neutralization reactions. Similarly, ethanoic acid reacts with bases, like sodium hydroxide, to form salt and water. For example, when ethanoic acid reacts with sodium hydroxide, it produces sodium acetate and water. Now, connecting this to esterification again, when a carboxylic acid reacts with an alcohol in the presence of concentrated sulfuric acid, they form an ester and water. This process is key to producing many esters. And speaking of acids, a solution containing about 5 to 8% ethanoic acid in water is what we call vinegar. It's a common household item, but it's actually a dilute solution of acetic acid. Finally, to sum up some properties of ethanoic acid, also known as acetic acid, it's a colorless liquid that has a pungent smell and a sour taste. These properties make it easily recognizable and useful in many applications. When soap is dissolved in water, it forms these spherical structures called micelles. In each micelle, the soap molecules are arranged in a specific way. The hydrocarbon, or nonpolar part, points towards the center, while the ionic, or polar part, faces outward. This arrangement is crucial because the hydrocarbon core is able to dissolve dirt, oil, and grease, effectively trapping them inside. The micelle then forms an emulsion, which can easily be washed away with water. Now let's talk about the cleansing action of soap. A soap molecule has two distinct parts. The long hydrocarbon chain is hydrophobic, meaning it's water-repelling and soluble in oils and greases. The shorter ionic part, on the other hand, is hydrophilic, water-attracting, and is insoluble in oil and grease. This structure is what makes soap so effective. The hydrocarbon tail binds with oily dirt, while the ionic head interacts with water. The overall process allows the dirt to be lifted from surfaces and emulsified into tiny particles, which are then rinsed away with water. For example, sodium stearate, with the chemical formula C17H35 is a common soap. It's a long-chain salt of a carboxylic acid, long-chain sodium or potassium salts of these acids. So, in summary, soaps are designed with this dual structure to effectively break down and remove greasy dirt, making them a powerful cleaning agent. Let's take a closer look at the differences between soaps and detergents. First, soaps are essentially sodium salts of fatty acids. They have been used for centuries and are biodegradable, meaning they break down naturally and don't pollute the environment. However, they have a limitation when it comes to hard water. Because soaps form insoluble precipitates with calcium and magnesium ions found in hard water, they don't wash as effectively in such conditions. On the other hand, detergents are different chemically. They are sodium salts of sulfonic acids. This small but important difference means that detergents perform much better in hard water. Unlike soaps, detergents do not form insoluble precipitates with calcium and magnesium ions, so they wash well in both hard and soft water. Now, looking at their cleaning performance, soaps tend to clean well only in soft water. Their effectiveness drops in hard water because of those precipitate issues I mentioned. Detergents, however, can clean effectively regardless of whether the water is hard or soft. This makes detergents generally more efficient cleaners. Another key point is biodegradability. Soaps are biodegradable, so they are environmentally friendly and don't cause pollution. Some detergents, however, are non-biodegradable, which can lead to pollution problems. So overall, while soaps are eco-friendly and effective in soft water, detergents are more versatile and powerful, especially in challenging water conditions. This distinction is important when choosing the right cleaning agent for different situations.